Now, one of these things that has to happen with these is the sums of the squares of these numbers. That's the dimension of the representation. The one-dimensional, that's A1. One-dimensional, that's A2. And then two-dimensional, they almost always use the letter E to indicate something that's two-dimensional. And you know, when you do E, you know, it looks 3. I mean, maybe they just break that one out of there. So there's the E, right? That's not, you know, where did these letters come from? Like, but anyway, that's the E. The first group that gives you a three-dimensional one is in the cubic family, tetrahedral. We'll get to that later on. But the idea is that the sum of the squares of these, that's 2 squared is 4, plus 1 squared plus 1 squared, has to be in the order of the group. We'll see why that is very clearly when we do the rest of the reduction. Because we still have to split the idempotents out of this. That'll give us 2 more, okay? Then we need 2 nilpotents. So you're going to get 4 things out of that guy, and then you just have 1 more, and that makes 6. These guys are going to have just plain idempotents. They're not going to have any nilpotents. They don't need it. But this guy right here needs nilpotents because he's going to build a matrix. He has to have off-diagonal projectors. Ket-Bras, if you want to, you know, use Dirac notation. So that's kind of summing all of this up in a you know, quick little thing here. And I would also point out to you this little, I just said to you that the order of the group is the sum of these dimensions, L. We usually use the letter scrilly L. That's the total number of irreducible projectors right there. That means it's the total number of elements in the group, because the group is going to have a linear combination of projectors. So the sum of their squares is that. The sum of them to the first power, that's the number of irreducible idempotents that are mutually commuting operators. The number of mutually commuting operators. That's the rank of the group. The number of mutually commuting. Okay. Well, in this case, if I sum that up, I get 4. Okay? That's basically what we're talking about here. Is the diagonal projectors P11, P22, which split out of these guys combination. Okay. So I've got 3 things here. If one of them splits, I get 4. That's the rank of the algebra. This is an algebra. It is an algebra, but it's also called the rank of the group. It's not talked about very much, but these two are. This is a centrum right here. It's the sum of these things to the 0th power. That's the number of classes, or invariants, or irrep types, or all commuting operators, the number of all commuting operators that you can find here. And in this case, there are 3. And that means there's going to be 3 irreducible representations, because this is a dimension right here to the 0th power, admittedly. So you only count 1 for each of the irreducible representations and add that up, and you get 3. So that's the number theory behind the group theory.
It's the same L from the Hamilton. The same L from the Hamilton.
Let's see. I'm trying to think. You're asking if it's the same L
Kinda.
would be used.
Your leading coefficient, whether that correlates to an angular momentum or not,
Oh.
kinda does.
Or just I think it was just the order of each item.
That's it.
In
Yes.
the multiplication.
It is, in a sense, because it is asking how many do you have. That's what this one is asking.
And so what we were talking about was the rank back then.
The rank is a little more difficult in the sense that it really has to know the algebra, right? Because it's asking you for how many operators can you find that are mutually commuting. The way this would come up in quantum mechanics would be you have a desire to find all of the mutually commuting observables, right? For example, J squared and JZ, right? If you're doing the quantum theory of angular momentum for the first time, you use those are the for just the rotational thing, the maximal set of operators that commute with each other and can be therefore diagonalized together, right?
Simultaneous.
And then their eigenvalues can then be used to label the states, right? And the idea, the game you're playing there is to get all of the operators that you need to label your states completely. With a simple angular momentum in 3 dimensions, you need a total angular momentum and then also a z component. And that will label all of the eigenstates of, like an electron that was confined to a sphere. Now, you start letting it have radial oscillations, you need some other operator. Where do you find it? Lin's vector, the eccentricity vector, okay? And of those eccentricity vectors, there's one that commutes with L squared and LZ, epsilon z. So that makes you a complete labeling for the symmetry O4, which is the symmetry of the hydrogen Coulomb problem, non-relativistic problem. I don't know if that answers your question, but the whole idea of finding enough operators to label your states is part of any quantum mechanics class that's, worth a nickel. It's also very deep because it goes back to what we just did today, and that is find operators to label our base states without knowing what the eigenvectors are yet. That's to be found using this stuff. So
the question will become more clear when we fill in those other projectors, those nilpotent projectors that are missing.
Yeah, we need 2 more guys to finish the story here, because we've got 4 already. We've got 4 operators that let us. We haven't split these things yet.
Everything else is singletons.
Yeah, so we
except
still have
this.
to. Whenever you see a 2 in the first column, it means you've got 2 dimensions, and that this projector will split. So when I get 4 irreducible, that's unsplittable projectors, that's all the projectors I'm going to get from this group. Now I'm going to take those guys and I'm going to do a 1 times G times 1 equal G trick. That is, I'm going to take those 4 projectors on either side of a group element, okay? And I will produce for you out of that 4 objects altogether that will include the splitting of the projectors that we already have here. That'll be P11 and P22, and then the other 2 are P21 and 12, off-diagonal elementary operators. That will make 4 operators that are irreducible. Then you don't leave these guys behind, they're still in the game. That makes 6 operators altogether. 4 to deal with E, and 1 for each for A1 and A2 representations. So the energy labels then are complete. You have completely labeled the eigenstates that will come out of this system that has 6 wells deployed in the group slide rule that we showed first. That's what we're headed toward. But the first stage is done. This is for stage 1. Stage 2 is split the PE projector, and then stage 3 is get the additional 2 that come from that splitting. So that's why it's going to take 3 lectures to to, just describe completely the theory of D3. But once you've got that, you just do it to every other symmetry you can find.
Literally.
Yeah. Yeah, this stuff applies to every possible symmetry analysis that anyone has ever done. It's more than just group theory, it's algebra. Whenever you're doing projection operators, things like that, that's all algebra because they're linear combinations, right? Does that help at all?
Yeah. I mean, I think that was more than what I originally asked, but I mean, that was helpful anyway.
Yeah, just a heads up on what's coming. And of course,
We're trying to compare that or get a
we've
reference.
actually put these two extra lectures out there, so if you want to take a glance at them, you'll get a heads up and be able to understand it.
Give me a day to get the next two out. We had this one up early.
Yeah.
We don't have the next two posted yet, but we shall.
It's not too different from the previous year.
Yeah.
Well,
You can
I mean,
always run
sorry,
ahead that one.
previous biennial, we do this every 2 years, so 15. Go look up the 215 lectures, approximately same number.
Okay.
Numbers have shifted a little bit because we cleaned up a few
I'll
things.
show the link for that and then also Malvibes.
Well, I mean, I can find it in
Okay.
Yeah.
Cool beans.
It's on the master page, actually. Yeah, it lists the courses.
Yeah, yeah.
Just go there and look for 215, 2015.
Yeah, right about the sectional breakout, the lecture breakout.
Okay.